Our ultimate goal for what we're going to do today are the problems on the back. So why don't we have a look there? So what we're going to start working on today is we're given a polynomial in standard form, and our goal is to find all the zeros, and then eventually we're going to do some other analysis with it as well. But the hard work with this is going to be to factor this thing. Once we get it factored, we know what the zeros are going to be. You guys have practiced that already in your previous work. And we've sort of talked about looking at a graph and finding factors from graph. That was our Desmos activity that we did on Monday. And we're going to be utilizing our graphs a lot for these as well. So there are a lot of tools we're going to have to utilize. One is going to be looking at a graph. And when we look at a graph and we're looking to find factors, where are we looking on the graph? X-intercepts, right? You guys practiced that with your work last night. You looked at the X-intercept, and then you look at the behavior there. Is it crossing or is it bouncing? And that intercept is going to give you a factor, and the behavior will tell you whether it's a squared or a power of 1. We're going to learn some other tools that we can deal with as well. And then you're going to also be falling back on some tools that you're already aware of, like the quadratic formula and just general factoring skills. Okay, so a lot of moving parts to these problems, but let's start with kind of the basics. We need to know, in order to do this, we need to know about a couple theorems: the polynomial remainder theorem and the polynomial factor theorem. So have a read through this. I don't want to try and read this out loud because it's kind of messy as it is. You guys have any idea what the heck that's trying to say? Yeah, this is pretty typical math speak. When you get into your upper level math classes, you're going to have these books that are just full of these theorems, and then you're supposed to be able to just read it and know what they're talking about. So let's do an example to illustrate this. Okay, so I've got a polynomial. Here's a polynomial. And what this says is that if I divide my polynomial by x minus k, then the remainder is going to be f of k. Okay, so let's go ahead and find the remainder when our factor is divided. We're going to do part B first because this kind of goes along with this. So what is k for this particular example? Up here it says x minus k, so k must be what? So we're looking at -3 here. Okay. So let's go ahead and divide this polynomial by x plus 3. Now, can we do synthetic division for this? Yes, because we're dividing by a first degree polynomial. You can use synthetic division for that. I asked you guys to refresh yourself on synthetic division about a week and a half ago. I sure hope that you did, because we're going to be using it a ton in the next few lessons. All right, let's go ahead and do our synthetic division. -3 would be the root from the thing that we're dividing by. And then we need our coefficients. I'm just checking to make sure I didn't skip any powers, and it looks like we didn't. So my coefficients are 1, 3, -11, and 2. We'll probably be using synthetic division about 5 or 6 times today. And when we do this, I'm going to be moving pretty quickly through it. My assumption is that you know how to do synthetic division. As always, if you don't, please see me some other time for some support with that. All right, let's do this. 1 drops down. We always multiply by the thing out front. -3 times 1 is -3. Adding straight down gets us 0. 0 times -3 is 0. -11 plus 0 is -11. Times -3 gets us +33. Adding down, bless you, it gets us 35. What is the remainder? 35. All right. So the polynomial remainder theorem says that if we divide by this thing, then the remainder is 35. But really what it's telling us is that that remainder is also f of -3. In other words, if I were to plug -3 in for all these x's here and type that into my calculator, the calculator is going to spit out an answer, and that answer is going to be what? 35. So what this is basically telling you is synthetic division is useful to us not just for dividing things, it's actually useful to us for evaluating things. So in a minute here, we're going to evaluate this as 2, but let's talk about something else here really quickly. This is the polynomial factor theorem. Is x plus 3 a factor of my original function? Yes or no? It's not, because why? What does the remainder have to be in order for it to be a factor? It has to be 0. So that's the definition of a factor. If you can divide something by something else and there's no remainder, then you've divided it by a factor. So my reason is remainder is not equal to 0. So let's go do the same thing. We're going to use the same function, but this time we're going to evaluate at 2. So I want you to plug 2 into this equation and get an answer, but we're not going to do it by actually plugging 2 into the equation. We're going to do it using synthetic division because it accomplishes the exact same task. So I'm plugging 2 in, and I'm doing it by synthetic division. So same polynomial, go through your steps for synthetic division. Times 2 is 2, add them up is 5. Times 2 is 10, add them up is -1. Times 2 is -2, add them up is 0. So what would I get if I were to plug 2 in for all of these x and evaluate the function? We would get 0. Because 0 is the remainder. So the remainder is the value that you would get when you plug that root in. So in doing this, we've done 2 things at the same time. We both evaluated the function at 2. We've also divided the function by x minus 2. Since we got a remainder of 0, what's that tell us about its factor status? It is a factor. It is a factor because the remainder is 0. And because it's a factor, not only have we evaluated and found that it is a factor, we've also given ourselves a new way that we can write this function. This function is written up here in standard form. We have begun factoring this function. F of x equals, so this is going to be the same thing, just in a different format. We found that x minus 2 is a factor, so that is one of our factors. What would be left over if I factor that x minus 2 out? Oh, good for you guys. I think some of us have seen this before. It would be 1x squared plus 5x minus 1. So we have created a new version of this function. And I don't believe this factors any further, so we just also succeeded in factoring that polynomial. All right. So we're going to be doing a lot of this today. We'll be using synthetic division to factor out some value or some factors. And I want you to keep in mind that when you start with a polynomial that looks like this is a 3rd degree polynomial, every time you find a factor and you pull it out, you're going to reduce the degree of your polynomial. So we started with a 3rd degree polynomial. We factored out an x minus 2, and that left us with a 2nd degree polynomial. So the big idea is going to be we're going to find these factors and we're going to kind of shrink and shrink and shrink our polynomial down until we get it to something manageable. If I asked you to find the zeros of this function right now, you'd be able to give me one of your zeros really easily by looking at this factor. Give me one of my zeros. 2. There are 2 other zeros. They're going to come from this piece right here. How would we have to find those other 2 zeros? We'd have to use the quadratic formula. We'd set this equal to 0 and solve it. And I'm guessing we're going to get something irrational or possibly even complex. All right, you guys with me so far? So that's a basic introduction of what we're going to do. We're going to start sticking it together here in a minute. But before we do, we need one more tool. I checked with our Algebra 2 teachers from last year. They said they had seen this, but maybe just like a day of it. You guys remember the rational roots theorem or rational zeros theorem? There's a P list and a Q list. Yeah. Oh, why are we groaning? This is not a bad thing. It is kind of messy, I'll tell you. All right, so here we go. What we're going to do here with this is we're going to create a P and a Q list. So the constant term is going to give you your P lists. So I'm going to make my P list here next to my constant term. And the P list is just a list of all the factors of that constant term. So what integers divide into 4? Well, there's 1, obviously. 1 goes into anything. 2 goes into 4 also. And then 4 goes into itself. That's kind of a nice P list. There's only 3 options there. Q list, on the other hand, is a little bit bigger. My Q list is going to be a list of all the factors of my leading coefficient, which is 6. So, well, 1 goes into everything. 2 also goes into 6. 3 goes into 6, not 4, not 5, but 6 does. So we've got 4 factors there. So what we're going to do right now is generate a P over Q list. I'm color coding these. Now, the P over Q list is going to consist of all possible combinations with these numbers on the top and these numbers on the bottom. Those of you who know combinatorics, tell me how many different fractions could we potentially make with these two lists? I heard it. 12. We could make 12. Right? Because each of these could have each of these on the bottom of it. 3 times 4 is 12. So I'm going to go ahead and set myself up 12 fractions. By the way, they can be positive and negative, but I'm not going to write it in front of every one of them. I'm just going to write it out front. So 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. And we're going to generate our list. And this is a little tedious, but it's not that bad if you keep yourself organized. The way I like to do it is I like to start with my Q's. I know I'm going to have 3 versions that are going to have 1s on the bottom, and 3 versions with 2s on the bottom, and 3 with 3s on the bottom, and 3s with 6s on the bottom. Okay. So that's our list, but there's some redundancy in this list, isn't there? Some of these are already in the list. For example, isn't 2 over 2 the same as 1 over 1? That's a repeat. What other repeats do we have? 4 over 2 is the same as 2 over 1. 1 over 3 is the same as 2 over 6. What about 4 over 6? It's the same as 2/3, isn't it? So those are all repeats. So we're going to now just generate our final P over Q list. And when we do this, you guys are not going to be huge fans of this, but it's good practice. We're going to do this in increasing order. So I want you to start with the smallest one. So from smallest to largest. And when you do this, I recommend that you kind of check off the ones that you've got on there. So as I look through here, my smallest one, I think, is 1 over 6. Don't forget your plus or minus, by the way, out in front. So 1 over 6. And then what would be next? 1/3. 1/2. Should be checking these off as I go. And then let's see, 2/3 is less than 1 still. 4/3 is bigger than 1. So then I go to 1. 1 over 1 is just 1. And then 4/3 is a little bit bigger than 1. And then I got 2 and 4, and that wraps up my list. Bless you. You guys remember doing this before? Was your teacher a big meanie pants last year and make you write them out in increasing order too? Oh, really? Okay, good. I don't feel so mean then. All right, That's good practice. What does all this mean? Why do we do this? Let me ask you a question right now. For this polynomial, I don't know anything about it. I haven't graphed it or anything. But here's a question. Is 3/4 a zero of this polynomial? Is 3/4 the zero of this polynomial? The answer is no. How do I know it's not? It's not on the list. If it's not on the list, it's not a zero. Is 7 a zero of this polynomial? No, absolutely not. Is 2 a zero of this polynomial? It's possible that it could be. Not for sure, but it could be. Also, -2 could potentially be a zero of this polynomial. But if I asked you if 5 was a zero of that polynomial, you would say absolutely not. There's no way that it could be. So this gives us a list of potential rational zeros. Now, here's the thing. Is every zero in this list? No, because we could have zeros that were like the square root of 3, and that square root of 3 is not rational. Okay, that's an irrational number. So this doesn't give us a list of all of the zeros. It just gives us a list of all the rational zeros. But it's going to become useful to us here in a second. Okay. So this helps us to eliminate things that could not be potentially part. Okay, question. Thanks for your patience. No. Okay, so thank you for asking that question. That's a really important question. Are we going to check all of them? So there are some pre-calculus classes where they're going to give you a big, long, nasty polynomial like this, and your job is going to be to, without a calculator, find all of the zeros for this thing, okay? Which would mean that you would start going through this list and synthetic dividing every single one of them out until you came up with how many zeros are there in this thing. It's a 4th degree, so there are 4 zeros. We'll learn about that later. Until you find 4 of them. Maybe you get lucky and find the 4 right away. Or maybe you have to try. I mean, how many possibilities do we have here? 1, 2, 3, 4, 6, 7, 8, but then positive and negative. There's 16. You could potentially be doing 16 long divisions to get all the way through that list. Okay. So now there are some tricks that make that a little bit easier. Okay. That's not this class though, because in this class, we've got access to technology. We're going to accept that we have access to technology. We're going to use this guy to make our job a lot easier. Okay. Now this list is still going to be useful to us, but it's not going to be useful to us in the same way that if we didn't have a calculator, right? So if you ever find yourself stuck on a desert island without a calculator, and you're for some reason trying to find zeros of a polynomial, then you're going to have to use the list. But we've got our calculator. So thank you for that question. Yeah. All right. We ready, guys? So we're going to flip over. We're going to do our first problem back here. And I'm going to lead you kind of through the process. Our ultimate goal is to find all of our zeros here. Okay. So our ultimate goal is to find our zeros, and then we are going to factor them as well. So let's go ahead and set up our answers, our zeros. Does anybody know how many zeros this polynomial will have? It's going to have 4. Are all those zeros going to be rational zeros? Well, I don't know. I don't know that yet. Maybe, maybe not. But I know there's going to be 4. Some could be repeated. You know, if we get a multiplicity of 2, that's really counting twice, but there's 4 zeros. So how are we going to find it? So our first step is going to be to graph it in the calculator. Okay, because we know how to find zeros sometimes from a calculator screen. So our first step is going to be to graph it. And for the sake of our notes, I'm going to actually make a sketch of the graph. Just a really small, rough sketch of the graph. But let's go ahead and type this in to our calculator under Y1. And I'll tell you that I have learned when I do these problems that I need to double and triple check that I didn't make any typos when I put the equation in, because there's nothing worse than spending like 10 minutes doing a problem and not being able to get it to work out, and then coming back and realizing that you turned a plus into a minus in the very first step. I've done that plenty of times. So I'm going to just double check and make sure that I don't have any typos in here. I think I'm good. Then I'm gonna go zoom 6 to get myself back to my standards viewing window. Hey, all right. All right. So I'm gonna make a rough sketch of this. It looks like I need to go to the left by like 3 or 4 tick marks. 1, 2, 3, 4. 1. That should be good. What I'm seeing on my graph is looks like I might have an intercept right around 3. How could I be sure that there is an x-intercept at 3 and not just like super close to 3, -3 rather? Second, so let's go second. I could use a table, but I'm gonna go second calc value because it's really easy. Type in -3. Guys, you want to get in the habit of using this second calc value thing. It's pretty useful. And I'm getting 0. Yeah. Pressing zoom and pushing what? Trace. Oh, look at that. I didn't know that. Well, that's super useful. Thank you. That's a shortcut. You don't have to do second calc value. You can just do trace and then type in the number that you want and hit enter. And it'll tell you, oh, hang on now. Yeah, so 2 is not. I don't know why I put 2 in. I meant to put -1 in. -1. I'm getting 0. Hey, nice. Thank you for that. That's a great shortcut. All right, so I found 2 zeros. I know I have tested. I know for a fact that I've got a 0 at -3, another one at -1, and then there's another in betweener between 0 and 1. And I'm just going to make a rough sketch of what my graph would look like for the sake of our notes. We are bouncing off here. See something like that. So we verified using our calculators that we do have a 0 at -3 and at 2. And what's special about this 0? I'm sorry, why did I write 2? I keep saying 2 and writing 2. It's a -1. What's special about this 0 at -1? The multiplicity is 2, which means I need to include it in there twice. It counts twice. And then we're missing another one that's somewhere between 0 and 1. So how are we going to find that other one? Well, we could do some synthetic division and divide out all 3 of these and see what we have left over, but that could take a while. There's an easier way to do this. Why don't we look at our P over Q list? Okay, now I'm not going to write the whole thing out. So stick with me here, guys. Don't miss this, all right? My P values would be what? What are my factors of 9? 1, 3, and 9. And my Q values would be what? 1 and 5. What fractions can you make out of those 2 things that might fall somewhere between 0 and 1? Remember, it's going to be P over Q. We could do 3 over 5 or 1 over 5, right? Our possibilities from this that could potentially be in there would be 3/5 or 1/5. Those are the only 2 that might be in that area there. So let's go back to our calculator and we'll do, and thanks to Jacob, I know a shortcut now, trace, and then I'm going to type, I think it's probably 3 over 5, if it's either of those, and I'm going to hit enter, and what am I hoping to see for my Y value? Hey, guess what? We found our other one. Huzzah. So here's our other one. It's 3/5. We checked it in our calculator. It does work. We found all 4 of our zeros. Question? Yep. Yes. All right. So we're kind of starting to put together an algorithm here. So thank you for that. So yes, we use our graph to find as many zeros as we can. We verify them with the trace, right? And then if there's any in-betweeners, we look to our P over Q list and see if we can catch any more that way. Now, what we're going to see in the next one is that there are going to be some additional ones, and we'll learn what we would do if we don't catch all of them. But in this case, we know we got them all. Let's write out our function in factored form. This part is a little bit tricky, so stick with me here. Leave a little bit of space before your first factor. Spoiler alert. X plus 1, I'm going to include twice, right? Because I have -1 as a root twice. So I'm going to just do x plus 1 squared. Then I'm going to have x minus 3 over 5. But we got to be a little bit careful because this version is supposed to match the one that we had originally. And I'm going to say that right now that's not going to happen. Because look at this lead term. I would need a 5x to the 4th. If I multiply an x times an x times an x times an x, am I going to get 5x to the 4th? No. So I need a number in front here. What should I put in front of there? 5. A 5 would do it. Okay, again, let me back this up. I know that I need my lead term to be 5x to the 4th. We can find our lead term by just multiplying our lead terms here. There's 1 here, x times x times x. I included it twice because it's squared. Times another x. Right now, my lead term would be just x to the 4th. I need 5x to the 4th. So we'll just throw a 5 out here, and that'll fix it. So we got to make sure we match that lead term. I'll tell you that if you were to look at an answer in your book, it would not write it this way. It would write it like this: x plus 3, x plus 1 squared, and 5x minus 3. That's how your book would give the answer. But both of those are technically correct. None is really better than the other. What's the difference between, what's going on here? Why are these different? So I took the 5 that was out front and I multiplied it into this term. 5 times x is 5x. 5 times 3/5 is just 3. Okay, so either one of those would be correct for a factored version. Who's got questions? All right. If you write really small, you might be able to fit this next one into this space here. Okay. But if you're a big writer, you might want to put this. This is why I asked you to have some scratch paper out. So I'm going to start it on here, but there's a good chance I'm going to need to, at some point, go over to some scratch paper. We're going to start this one off the same way we started off the last one. So just to reiterate, and thank you for starting to put together this algorithm for us. We're going to start with our graph. We're going to see what we can pick off the graph. If we have any in-betweeners, we're going to use our P over Q list and see if we can find some more zeros. Now this time, I'm going to, spoiler alert, we're going to find that we don't get them all. So we're going to have to do a little synthetic division to finish it up. So here we go. We got this. We got this. So I'm going to make a sketch of my graph, and then I'm going to type it into my graph, and we'll fill in our sketch. And then I'm going to double and triple check that I don't have any typos in here. Good. Graph it and see what we see. Oh, there's a betweener. There's a couple more between. Oh, it looks like 3 might be one of them. 3 does work. I'm going to try trace 3 and hit enter. And my graph is telling me that, yeah, 0 is my y coordinate. So 3 is 1. So we're seeing, we got a nice intercept at 3, and then we've got some in-betweeners. So let me just make a rough sketch of this. All right, so we got an intercept here at 3. There's one kind of in between 0 and 1, another one between 1 and 2, another one between -3 and -4. They all look like they're singles because we're crossing over at each of them. So we were able to get 3 from the graph, and we verified that 3, 0 is on the graph. So we're very confident in that. Let's see if we can pick up another one at least. So it would be nice if we could get at least one more off of the graph. So I'm going to look at my P over Q and see if that gives us some help. So my P list is going to be kind of long this time. What all goes into 30? 1, 2, 3, not 4 doesn't, but 5 and 6 do. 7, 8, no, 9, no, 10 works. 15 goes into 30 and 30. That's a pretty huge P list. Thank goodness we don't need to list out everything. And then my Q list is going to be just 1 and 3. Oh, that's nice. All right, so I'm looking for some potentials that could give me something between -4 and -3. So between -4 and -3, I'm looking for in between there. What could potentially be -10 over 3 would be, yep. Any other fractions I could make out of that would be between -3 and -4? I think that's it. All right, so let's check and see if -10 over 3 works. Trace -10 over 3. We're hoping for a 0, fingers crossed. Ah, bummer. That's really far away from the 0. Okay. So that doesn't work. All right, let's see if we can catch this one between 0 and 1. What fractions can we make between 0 and 1? 1/3 and 2/3, and I believe that's it, right? Does one of those work? Trace, try 1/3. Ooh, hang on here. What happened? My window got messed up. Zoom 6. Dun, 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 dun. All right, I'm trying 1/3. You guys said it doesn't work, but I'm gonna try it. 1 over 3. Nope. Let's try 2 over 3. Hey, 2 over 3 works. 2 over 3 does work. So we got 2 over 3 as one of our zeros. That's great. Let's see if we can catch this this one over here. Then we would only have one left over. That would be ideal. This one's between 1 and 2. What fractions can I make out of my P over Q list that are between 1 and 2? 5 over 3, and that's it, right? 5 over 3 is my only option, so let's see if that works. Fingers crossed, give me a 0. Come on! No? Ah, wah, wah, wah. All right. Okay, well, we got 2. We got 2. That's good. That's good. All right, I want to pause here for a second and make sure that we're all on the same page. You guys okay with what we've done here? We graphed it. We found that 3 was a 0, and we verified it with our calculators. We also had 3 others that were kind of in between some things. So we didn't make our whole P over Q list. We were just looking, could I make a fraction out of these that fits somewhere in between -4 and -3, between 0 and 1, between 1 and 2. And we were able to find 1. So that's good. That means we're missing 2 more zeros, and I'm going to say that those 2 zeros must not be rational zeros. Because if they were rational zeros, they would have ended up in this list, right? So they're probably going to be something either with an I in it. It's going to be a complex, which I'm telling you it won't be. We won't get to that till next week. Or it will be something with a square root in it. So more than likely, we're going to end up doing a quadratic formula. So here's what we're going to do now. We're going to take this big polynomial and we're going to start factoring some stuff out to shrink it down. Okay. So we're starting with the 4th degree. We're gonna factor out x minus 3. Then we're gonna factor out x minus 2/3, and that's gonna get us down to a 2nd degree polynomial, a quadratic, and then we'll be able to use our quadratic formula. So let's do it. So I'm gonna I wouldn't normally write this down, but since this is our notes, let's write what we're doing. So factor out and x minus 3. I'm going to do the 3 first. So we could do x minus 2/3 first. That's a great question. I will usually save more complicated ones for later because they shrink every time you do them. So if you got an easy one, like a 1 or a 2, like I usually hit that first. Then you won't have to deal with the fractions for as many terms. All right, my coefficients are 3, -5, -31, 67, and -30. And we're fairly certain this is a 0, so what are we expecting our remainder to be? 0. And what's going to happen if we get something other than 0? Well, we might shed a quick tear of despair, but then we'll regroup and we'll say, okay, there's a mistake someplace. Let's go find it. All right. Oh, let's see here. What is that? 19? -19? -19 times 3 would be 57. -57, right? And that gives us 10 and 10. Oh, good. We did get that 0. No tears of despair. Okay, so, and again, I probably wouldn't write this down normally, but since this is our notes, hey guys, stick with me here, please. Don't miss this because this is important. Remember, I said it's important to know not just how to do this, but to know what you're doing. So please don't miss this. This is where my students tend to start struggling a little bit with this. There is a process that we're doing here, but I need you to understand what we just accomplished by doing this. What we did was we took this function and we can now rewrite it as a factored version, not completely factored, but partially factored. X minus 3 is one of our factors. And the other factor that we have is 3x to the third plus 4x squared minus 19x plus 10. So by factoring one thing out, our remaining factor gets a little bit smaller. Now it's a 3rd degree instead of a 4th degree. So what we're going to do next is we're going to factor out the other 0, which would be correspond to a factor of out. I'm trying to write and talk at the same time. Factor out what? 2/3 would give us x minus 2/3. Now, before we do this, I want to give you guys the cheat code for multiplying by fractions. Let me get this set up and then I'll give you my cheat code. Now, by the way, when we do this, we are going to use this smaller polynomial. We're not going to go back to our original one. We're using that smaller one, the reduced polynomial. All right, so here's the cheat code. You guys ready for this? When you multiply something by a fraction, you are doing 2 separate operations. You're multiplying by the number on the top and you're dividing by the number on the bottom. You can do those 2 operations in any order that you want. A lot of times when you're trying to do this mentally, it's faster to divide by the 3 first and multiply by 2 at the end. Okay, so keep that in mind. So when I drop this 3 down here, and I'm multiplying 3 times 2/3, you can think of it as divide by the 3, get you 1, multiply by the 2, gets you 2. 4 plus 2 is 6. Take that 6, divide by 3 first, and then multiply by 2. So divided by 3 is 2, times 2 is 4. -19 plus 4 is -15. Now, you might think that's tricky to multiply by 2/3, but just do your division first. Divide by the 3 first, you're going to get -5. Multiply by 2, you got -10, and we're good. So a lot of times people kind of freak out when they see a fraction and they're like, man, I'm gonna have to multiply by a fraction a bunch of times. It's not a big deal. And if you know this is a 0, you're always gonna end up with whole numbers in this part of it anyways. All right, so what we have created now, I'm gonna actually skip down to the bottom here. We can now write this function as a product of linear and irreducible quadratic factors with real coefficients. I copied this out of the book. This is going to come up in your instructions. That function in that format is going to be f of x equals, you got x minus 3. You've got x minus 2/3. And you've got our leftover factor here, 3x squared plus 6x minus 15. And let's really quick check. I did leave a little space out in front in case I need to put a coefficient in there. Check our lead terms and make sure that we're going to get, what should we be getting for our lead term? We want a 3x to the 4th. If I multiply out my lead terms, am I going to end up with a 3x to the 4th? X times x times x, 3x squared would give us, okay, so we don't need a coefficient on that. Now, we still haven't found our last two zeros. Where are they going to come from? They're going to come from this quadratic factor. So this is where I've run out of room. I need to go onto my scratch paper now, but I need to do the quadratic formula to find my zeros for this. And hey, what do you notice about all of the coefficients in that quadratic there? Yeah, so keep in mind when you're solving a quadratic formula, you're solving the equation 3x squared plus 6x minus 15 equals 0. What could we do before the quadratic formula that would make this equation simpler? We could divide both sides by 3. And we would have a simpler version of the same equation that would just be x squared plus 2x minus 5 equals 0. And then we can do the quadratic formula to solve that. Now we only divide by 3 if we're solving. We can't divide these by 3 in the factor. Only once we can get it into an equation so that it equals 0. All right, so let's do our quadratic formula. You guys are going to be pros with the quadratic formula by the end of this chapter. For 20 is 24. Make sure you're splitting it up into two separate fractions to avoid that common mistake. Both things should be over 2. Root 24, that's 4 times 6. Square root of 4 is 2. Get it? Nice. Common mistake would, people are going to want to cancel this 2 with this 2 down here. You can't do that because of this plus or minus in there. Yeah, so that's why I highly recommend when you're doing the quadratic formula, when you get it down to the point that it's just a number inside and outside of the square root, split it up into 2 fractions and then simplify them separately. You won't make that mistake again. This is going to be another one of those algebra 1, algebra 2 skills that we're not going to be spending time in class covering. If you're not sure how to take root 24 and turn it into 2 root 6, please see me. I can get you up to speed on that really quick. So we're getting 1 plus or minus root 6. So let's go back up and finish our answer up here. One of our zeros is 1 plus root 6. Oh, sorry, negative 1 plus root 6. And the other one is negative 1 minus root 6. And then I want to write down our final version of the factored form. When they say a linear factorization, they're looking for linear factors only. This one we wrote at the bottom is not a, this is not a linear factor. This is a quadratic factor. So my linear factorization would look like this. It's going to be f of x equals, it's going to be x minus 3 and x minus 2/3. Those are both linear factors. And then we're going to have x plus 1 minus root 6. And then we're going to have x plus 1 plus root 6. When you get that written down, I want you to make sure you're feeling comfortable with why that's a plus after the x in both of those. Are we okay with why that's a plus? Can someone tell me why it's a plus? Right, remember when we turn it into a factor, we're doing the opposite of the 0. So this was a negative with plus or minus. We want to make this a positive with a plus or minus. Let's double check and make sure. Do we need a lead coefficient out in front of this thing to make it match our original? Our original had a 3x to the 4th. Are we going to have 3x to the 4th? X times x times x times x. No, we're not. So we do need to put a 3 in here for this one. If I were doing a test right now, what would be a really quick way to make sure that I came up with the correct zeros? We've already got it graphed, right? So I could go back to my graph here and I could use my newfound shortcut. I'm going to do trace and I'm going to type in -1 plus square root 6. Okay, my calculator is going to turn that into a decimal and then it's going to evaluate there. What am I hoping it comes up with for y? 0. And I'm not going to be too upset if it's like something e -6, right? Oh, it's actually 0. That's great. That's great. I'm going to try this one also. That would only take me a second. -1 minus root 6. Let's make sure that also works. Yep. So now this one gave me that weird answer, but we see e -11. We know that's your calculator doing its best to tell you 0. Good calculator. You did your best. And then if I really had time and I wanted to make sure that my factorization was correct, I could go into my calculator. I could type this whole thing out in y2 and make sure that it perfectly overlaps the original one, right? All right. So there's a lot of moving parts here, folks. Let's take a step back. Let me answer a question first. Go for it. Okay, I'll have a look at it here in a second. Folks, it's a good idea to step back and just remind ourselves of the whole process here because there's a lot of pieces, okay? So first thing we're going to do is we're going to look at our calculator. We don't have to make the P over Q list and guess and check our way through because we're going to get some clues from our calculator. And we found a nice solid clue when we saw that intercept at 3. We know that was going to be a 0. We saw 3 other intercepts that were kind of in between points. So we looked to see, could we make some fractions out of our P over Q list that would fit in those spots? And we were able to find one other by verifying on the calculator that fit in there. So that got us 2 zeros. All right, at that point we were stuck. We couldn't find the last 2. So what we needed to do was do some synthetic division to factor out those 2 factors that we had found and get it down into a factored format that we could then use the quadratic formula to solve. So I'm going to tell you in this class, this is going to happen fairly regularly. You will usually, in this class, you'll be able to find all but 2 of your zeros by looking at the graph, okay? Because once we get it down, I need it to get down to something that everybody's familiar with solving. If it's to come down to a cubic, we don't really know how to solve a cubic right now, okay? So you'll be able, so in general, either you'll be able to see them all your zeros on the graph, or you'll be able to see like all but 2. All right, what questions do you guys have? How are we feeling about this? Yeah, question.
So, like factor out like the x minus 3. Oh, -8 with the
right. So when we're dividing by x minus 3, we put the root. Or the 0 up there, yeah. So set it equal to 0 and solve, that's the number that you put up there. Yep. Mm-hmm. Mm-hmm. Exactly. And then so once we get our zeros from our graph, we use synthetic division to factor out those factors that correspond. And then we just hope that we can get it down to something that we can solve. We were able to get it down to a quadratic, and we're like, oh, cool, I can finish it up with the quadratic formula. Yeah. If you, so like, let's say you get all of the zeros off your graph and you come down and you're still stuck at a cubic. We don't know how to do that yet. Now we will see some, I think there's one that comes, thank you for asking this. I think there's one that comes up in the homework where after you do your synthetic division, it comes down to like x cubed minus 8 is your last factor. We can't actually solve that. X cubed minus 8. So you could set it equal to 0 and solve it. X cubed minus 8 equals 0. And then x cubed equals 8. And then take a cube root on both sides. The cube root of 8 is 2. So you would get 2, and it would actually be a triple. Yeah. I don't know if that's going to come up or not. We'll see if that comes up. We'll see if that comes up. Yeah, but for right now, you should be, if you're ending up at something bigger than a quadratic, then you're probably missing a 0 on the graph. Okay. All right, you guys did awesome today. I'll put the assignment up on the screen and we can get started on it. I got a little chunk of time. 12 minutes.